It simplifies thinking about circuits if we can replace a few resistors altogether with one resistor which has the same effect as all those combined. And that's what we call equivalent or total resistance. Answer the question that you can see here. Pause until you've done so. The question is saying, if you have a number of resistors in series and you replace all of them with a single resistor of equivalent resistance, will that equivalent resistance be lower than the lowest resistance of the components or greater than the highest resistance of the components? For a series circuit, the answer is that it will be greater than the highest component. How great would it be? In the case of resistors in series, the equivalent resistance is very easy to find. All you do is you add the resistance of the individual resistors. So get the equivalent or total resistance of these three resistors. Pause until you've done this yourself. 1 ohm plus 5 ohm plus 25 ohms equals 31 ohms. So you can replace those three resistors with a single resistor. As long as it has a resistance of 31 ohms, it will have exactly the same effect as the three. Well, what about if we place the resistors in parallel to one another? Pause the movie while you answer this question. The question is asking whether the resistor, which is equivalent to these three in parallel, would have a resistance less than the lowest of the components or more than the highest of the components. And the answer, perhaps surprisingly, is that the equivalent resistance in a parallel combination would have a resistance less than the lowest resistance of the components. Why is that? This is easy to understand if you think about the water analogy, because adding resistors in parallel is just like making the pipe thicker, or adding other pipes on the side that the water can choose between. Later you will learn how to calculate what the actual value of the single resistor is that has the same effect as a number of resistors in parallel. Let's get back to series circuits. For each of these four circuits, calculate the equivalent resistance. You can also call it the total resistance. And then also calculate the fraction that each resistor makes of the whole resistance of that circuit. Pause until you've done this yourself. The total or equivalent resistance is found by simply adding the two resistors' values to one another. 3 plus 3 equals 6. 2 plus 4, 6. 7.5 plus 7.5, 15 ohms. And 5 plus 10, 15 ohms. What about the fraction that each makes of the whole? In A, each makes up half of the whole. The whole is 6 ohms. The first resistor has a value of 3 ohms, so 3 out of 6 is a half. In circuit B, the 2 ohm resistor makes up a third of the total and the 4 ohm resistor 2/3. The total resistance is 6 ohms, so 2 out of 6 is a third. 4 out of 6 is 2/3. In C, again the resistors each make up half of the total, like in A. Although, of course, the total is not the same. Here we have 15 ohm total, in A we had 6 ohm total, but in both, each resistor makes up half of the total. In D, one resistor makes up a third of the total resistance and the other 2/3, which again is similar to B. So although the total is different, 6 ohms in B and 15 ohms in D, the ratio between the two resistors' values is the same, namely 1:2, meaning that one of the resistors is double as resistant as the other in both cases. As you will see later, the current strength through the whole circuit is affected by the total resistance of the circuit, whereas the voltage distribution, or the potential difference across each resistor, is affected by the fraction that each resistor's resistance is of the whole, or put another way, the ratio of resistance between the resistors.